Okay, thanks for coming this afternoon. As I said, I'm doing Netscreen the Dead, which is basically an outline of developing Trojan firmware for Juniper Netscreen devices. That's me. That's kind of how I feel after a flight from New Zealand, which touched down yesterday. So if I fall asleep halfway through, just shout. I'm a security consultant for Aura Software Security down in New Zealand. Primarily interested in infrastructure and reverse engineering. So today, my talk really arose out of work I was doing for a client, looking at their perimeter defenses, their Netscreen firewalls, and they didn't have subnetting, they didn't have a network management, everyone could see their devices, and I was trying to persuade them that that was not a good idea. Their response was that they felt that anyone who gained an admin password or somehow got on the box, they would leave a trail, they would change the config, they were comparing configs, so they would quickly pick that up and spot it. So I really set out to prove that you could develop a Trojan firmware which would be stealthy, you would be able to change the config without anyone seeing it, and you would be none the wiser. So it's not a talk about an exploit of Juniper, although I think it outlines some security weaknesses in Juniper Netscreen. It's really, the primary attacks are obviously if someone has gained the admin password by whatever means, or the supplier, so who's supplying the device to you, who's making the device, and obviously insider attack as well, a malicious admin themselves. There is the possibility of a man-in-the-middle attack, so if someone's upgrading the firmware, uses TFTP, so you could intercept that and inject your modified firmware. And as I said, the goal is really hidden root control of the appliance. So I'll talk about the reverse engineering of that, how you modify it, how I did it, and I'll also do a demo for you of installing my Trojan firmware on my Netscreen I have here. So the Netscreens, Juniper have a couple of devices, or a couple of product lines. The one I'm talking about is the Netscreen devices. They range from small, like this one, which I'll use today, up to telco size, the NS5000. They have another product line which uses operating system called GNOS, which is based on FreeBSD, which is not what I'm talking about. These devices and the Netscreens they have Common Criteria and FIPS certification, and they run a real-time closed operating system that they call ScreenOS. And if you were at FX's talk earlier, it is similar to the iOS, so it's a one big executable running on the device. And the model I'll be using today is this little one here. It's the NS5XT. It's a PowerPC processor, 64 meg flash. It's got serial console, telnet, SSH, all that kind of stuff. And in fact, to find out it's a PowerPC, I really had to open it actually. There's a little sticker. Warranty void if removed, so I left that sticker on there. Didn't want to void my warranty. So really looking at firmware attacks, there's two approaches. There's the live debugging approach. So you need a remote debugger over a serial line. And the other approach is trying to somehow obtain a dead listing of that executable that will be running on the device. I'm basically using disassembly and a hex editor to try and work out what's going on. And just before I talk a bit more about it, PowerPC, if you don't know, I hadn't done any PowerPC before this project, so in some respects quite a bit simpler than Intel. It's got a fixed instruction size, all instructions are 4 bytes. It's a flat memory model, which is quite nice. 32 general purpose registers. There's no explicit stack, but there's conventions around which registers are used for that. And a link register for return addresses. The IBM PPC 405 Embedded Processor Core User Manual. That's a nice little bedtime read if anyone's interested in PowerPC. So my first approach was the live debugging approach. I thought that would be the easiest. But I don't have any PowerPC equipment, so I had to find embedded Linux development kit, which has GDB compiled for PowerPC, so it'll run on your Intel box and you can connect to PowerPC processors. Some of the issues, obviously, you don't have any source code, so you make up a GDB init for your remote GDB debugger, which basically references PPC registers and stack and what have you. I previously, many years ago, used soft ice, which I liked, so I made a custom GDB that would give me a kind of soft ice-like context whenever I broke. And it's fairly straightforward. You get a network connection to the Netscreen. You run that command, set GDB enable, and then you connect via your serial console, your remote GDB instance. So that's a little screenshot of my output from GDB context. To be honest, I couldn't get a lot working on this though. Memory dumps worked and querying memory addresses were good, but I couldn't get breakpoints or single stepping to work, so it was of limited use to me. It is possible to dump the whole of the firmware over the GDB, over the serial console. It's about 20 meg, takes a bit of time. That's one approach to obtaining the raw image. But instead I focused really on disassembly and a hex editor. So as a customer, once you've bought one of these, you can go to the website of Juniper and download all sorts of versions of firmware, basically, that apply to your device. So I went off and got as many firmwares from Juniper as I could. They supply it basically as just a binary blob, and you upload it to the device, and it does all the magic to install itself. And I did a comparative analysis, really, of all the different versions that I could find. And this is what I found. So there's a header to the firmware. There's a stub, which is looks a bit like a second stage bootloader. It contains some strings relating to LZMA compression, which is quite important. And then there's the vast majority at the bottom, the compressed binary update blob, which I'll just call bub. That's the vast majority of it. And they're about 4 or 5 megabytes in total, compressed up. Now, the header has some information. There's kind of magic bytes right at the beginning, the signature, a byte field with some system info, a field relating to the size of the firmware, and at the very end, a checksum. So the focus of the reverse engineering was really to, because at this stage I was a little bit surprised, to be honest. I expected that a security appliance firewall, UTM, telecom, telco grade NS5000, which ScreenOS runs on, would have encrypted firmware. But, and for me, this is one of the main design flaws. It isn't encrypted. It's just basically an obfuscated LZMA compression. So my focus was really on trying to fix the header in such a way that I could use off-the-shelf, freely available LZMA code to decompress it. And hopefully then I would be able to recompress it and after changing stuff and upload my firmware. So again, looked at lots of different headers from the different versions and looked at the LZMA spec. The LZMA has really 3 fields: options, dictionary size, and uncompressed size. And the bub header from the Juniper firmware has 3 fields, but they're a bit different. Has some signature bytes, has the options, has a dictionary size, but it's crucially missing an uncompressed size. So really, it came down to just those few bytes, really, and trying to work out how to modify those so that I could uncompress it. So I successfully did that. Effectively, I cut out the compressed chunk from the firmware. I found in the spec you could actually define the uncompressed size as unknown, so that's what I did. And then the bit that took the longest, really, reverse engineering, bit of fuzzing, and probably longer than I should tell you. Find out modifying the dictionary size from that value there, 002, 000 to the 8, enabled me to decompress the firmware using just open source LZMA utilities. So I was fairly happy at this point in that I could access the firmware. And the next stage was really, before modifying it, I wanted to test that I could recompress it and successfully upload it to the device. So again, I wanted to use off the shelf. I didn't want to code up my own LZMA. I'd probably just make mistakes. It'd take too long. So recompress it up, modify the dictionary size, delete the uncompressed size that the LZMA compression software would create, and then you can just basically append that to the original header and second stage stub. And that would successfully load up on the device. So at this point, I was quite excited. I was able to cut out the compressed firmware, uncompress it. I then did some modifications to it. I could then recompress it and upload over a serial line worked successfully. Unfortunately, uploading over the network at this stage didn't work, but keep that in mind. I'll come back to that. That's been fixed, not a problem. So at this stage, I can get access to the firmware and reload it onto the device after modifying it. So now I'll just talk a bit about what you do with the firmware. So compressed, it's about 4 or 5 meg. Uncompressed, it's about 20 meg. And at first, as I say, I'm very excited. I've got this uncompressed binary sitting there. I want to load it into IDA, but if I load it at address 0, I discover that all my strings are messed up, nothing's pointing in the right place, and I've got 20 meg of mess, basically. So again, some more reverse engineering, looking at the header of the uncompressed firmware. There's a header there as well with some magic bytes and some fields that look suspiciously like offset and address, and some other stuff as well. So in IDA, loading up that as the program entry point fixes all my strings and all my cross-references, and that's great. So I now have a correctly loaded binary, but it's all unknown sections at this stage. So using IDA, you can script, and using a hex editor and looking at then the disassembler, just some manual inspection, you can basically start to find the structure that I've outlined on the left there. This is a bit simplified, obviously. But again, the ScreenOS, one large executable, has a header, a code section, data section. I also discovered in there's the bootloader code and bootloader data, and that basically enables firmware to update any bootloader as it loads up. And there's a bunch of other stuff there as well, obviously web console files, certificates, all sorts of interesting little things. So using scripts in the ScreenOS code section, you can get it to automate marking sections as code and mark sections as strings in the data section. And once you start using strings, looking at error strings helps you name functions, and searching for good strings like string compares, file reads, file writes, logins, all that kind of stuff. And that helps you start to build up a picture of what the binary is and where the functions you're interested are located. The bootloader, too, you can cut that out and disassemble it separately. It has loading address 0, and again, same kind of techniques, obviously much simpler because it's much smaller, and there's some interesting functions in there. So at this stage, I can load up my own firmware, and I'm trying to think what you require for Trojan firmware. So I've really fallen on three key bits of functionality. You need to be able to install or upgrade the firmware over serial console, TFTP, or web. I want to be able to do it remotely. I need to maintain access, so I need some kind of backdoor login, and obviously a payload. I need to be doing something that I shouldn't be doing. So really, I need to be able to execute arbitrary code that I've injected into the binary somewhere, and potentially call Netscreen functions. ScreenOS built-in functions is probably a good idea. Save some space. So all the binary modification on the Netscreen that I did was basically just creating PowerPC assembly and then hex editing the binary. So the first one, as I said, initially I could load it up over the serial console, but not over a network. It would fail on a particular check. So the first bit of required functionality I need, installing and upgrading from anywhere. So it seems that over serial, the checksum isn't correctly checked or not checked at all, which enabled me to upload my first version. The checksum, however, in the web console, or if you SSH in, you can specify a TFTP server that you'll load up the firmware from. And when it loads it up from there, the process is slightly different. It loads it up, saves it to the flash, does some extra checks. So the checksum in the header, basically the ScreenOS calculates what the checksum should be. But if you load up a firmware with a wrong checksum, it prints out the bad checksum and says, oh no, that's bad. This is a bad checksum. I'm not happy with this. I'm not going to load it up. So we could reverse engineer the checksum function. We have the disassembly. It's all there for us. But I'm naturally lazy, and I thought a more interesting idea might be to create a firmware which, instead of printing out the bad checksum, would print out the checksum that it should have. So I have a checksum calculator firmware. So that's what I did. So effectively, I've created a checksum calculator firmware that I can load up, and I load up other firmware against it, and it tells me what I need to modify the checksum value to be so that it will correctly load. So we can now load firmwares over TFTP and the web interface, as well as serial console. So that's really the first bit of required functionality. And fairly straightforward. This is the code for it. Snippet of disassembly. Effectively, the header checksum and the calculated one are loaded up and compared. And there's a branch, and if they match, that's all good. I just modified the branch statement to basically move the calculated checksum into the register that the bad header checksum value was in. So then the checksum's always printed out to the console. Nice and simple. So second part of functionality, this is maintaining access. After disassembly and reverse engineering ScreenOS, obviously there's a whole range of ways of logging in. You've got serial console, telnet, web, SSH. But effectively, they all use one function which compares the password hash with the password hash stored on the device. SSH2 will fall back to password checks if you don't supply an SSH key, unless you've disabled the password authentication. Now, you could create a firmware which would always fall back to password, even if key authentication was enabled and password authentication disabled. I haven't done that, but certainly possible. What we find is that a 1-bit patch provides you a login with any password if you know the valid username. And it also has the interesting side effect of not allowing you to log in with the correct password. So this is the code. Again, fairly straightforward. Load up the two hashes, two separate registers, compare them, and equal if they match. Away you go. So again, the red code there is the simple modification. And as we see here, 1 bit just changing a 0 to a 1. Now we could modify the branch statement just below that and make it always allow you to log in if you wished. And really the last required functionality, which is probably the more interesting, so this is executing arbitrary code that I've injected into the binary. So the firmware, and you find this in most firmwares, they reserve space for more code they might add later. The code section contains a fairly large block of nulls, which is an ideal place to stick in your own code. So I created some proof of concept code, which I've injected into this null section. It's a bit like a message of the day function. When anyone logs in, from any interface, it prints out a string to the serial console. So we also have to hook some function, which in this case I've hooked the login function, which will basically branch to my new code, execute my code, and then obviously branch back using link register to or a fixed address back to the login code. So here I've got the PowerPC assembly of the proof of concept injected code, and just a shot of the binary where it's injected. So we set up some stack, load up a string, call a built-in ScreenOS function, which I've called print to console, fix a register for returning to the login function, clean up, and then back to the login function. So, as I say, this is proof of concept, really. There's all sorts of other things you could do. There's a whole bunch. The more disassembly you do, the more reverse engineering of ScreenOS you do. There's a whole bunch of inbuilt functions which you could use, which are all quite nice, and all very useful to an attacker. So, a bit of an aside about the bootloader. When I was doing this, I noticed that when I was loading up firmware, there was a line in the boot sequence which said image authentication ignored, which I thought was interesting. And I discovered that all this Juniper ScreenOS firmware is signed. But I think crucially, and this I think is the second design flaw, the certificate is not installed by default on the device. And an administrator can load one up. You go to the Juniper website and get your cert and load it onto the device. But they can also delete the cert as well. So it's not hardwired into the device, and it's freely accessible. Now the check for this image authentication, so once you load up a cert, effectively image authentication against the cert is enabled. And this check's done in the bootloader. So disassembling and reverse engineering the bootloader, we find the function where this is done, and we can modify this to, again, either authenticate all firmware or only non-Juniper firmware, if we so desire. So really the path for the attacker is, if the certificate has been installed by an admin, then delete it, install your bogus firmware, and reinstall the certificate. And that will mean that when the device reboots, it will accept the bogus firmware, because the check's done on every boot. And this is the bootloader code. Again, pretty straightforward patch. And a couple of options there in red. So we have a branch statement, which, if the firmware validation passes, it jumps. We could change that to either just a straight branch, authenticate all firmware, or just invert the logic so that only modified bogus firmware is authenticated. Yep. So, let's get it set up. I'll just demo some stuff on the Netscreen we have here. So I've got a little TFTP server running here with some modified images. This is the serial console to the Netscreen, and we also have the Netscreen interface. So admin at the moment on this, good strong password, and the usual menu items for setting up your device. So I'll show you everything just on the serial console because you get a lot more information on the serial console. You get a lot of messages printed out, which if you load images over the net or you log in there, you don't get as much information. So, oh. Once I log in. Okay. So I would just check this is the command to delete the certificate, which is installing this. So without the certificate, it's in the default state. So when you buy it, it's delivered to you, no certificate. What I will just show you though is loading up the image certificate. So there we go. And now I'll reset. So here in the serial console, we have an opportunity to load a firmware. Now I've got the cert loaded, so this will fail. I'll attempt to load up my modified firmware. There we go. So that's it, just copying across the compressed firmware, and once it's got it, it then unpacks it all. So there you see invalid DSA signature, bogus image, not authenticated. So, and there the image authenticated from the one that's stored on the device. So now we assume attacker has gained admin access, or the cert has not been installed by default, or your nice Juniper vendor or third-party support or Juniper supplier who has access to this in the default state. So we delete it, reset the device. So ignore image authentication. So saved on board. I'm not going to bother saving it. It's quite interesting because you can have a firmware on the device which is different from the one that's actually running. So now I have the opportunity to run the firmware. couple of seconds. Now, see what's happening here. The bootloader, which is modified to accept bogus firmwares, is now being uploaded on the device. So just up here, upgrading the loader. So even though I haven't saved the firmware to the device, and the firmware stored on it is a official Juniper, I've upgraded the firmware to allow me to load up bogus images. And also you'll see when I log in, the code that I've injected, which will print out some strings to the screen when you log in from anywhere. So there we go. And if I load in over SSH, and if you just watch the, there you go. So anytime anyone logs in, print out something to the screen. So obviously I've done this for purposes of demonstration, but obviously that code could be, oh, thank you. It is after lunch. Yeah, obviously that code could be doing anything and would be doing something far more subtle than that. Like emailing me your IP addresses or passwords or what have you. So now that that's done, I can reset the device. I'll just show the, so again, so the firmware stored on the device is still the Juniper firmware, but the bootloader has been modified to accept bogus firmware. However, I haven't uploaded the cert yet. Give me a second. There you go. And just before I load up the cert, the other functionality that's been patched in this is login with effectively any password. So I can just hit enter at that stage, and I'm in. If I go back to another SSH console, I can, as long as I know a username, which is pretty much always admin or administrator, I can type something like I love Juniper and log in. So I will just load up the cert. So as we're saying, so now, still saved on the device is Juniper firmware. Bootloader has been modified. I've loaded up a cert as well, so image authentication against the cert is enabled. And so once this is loaded up and unpacked, so there. So even though it has an invalid DSA signature, so that's just a function that I didn't need to patch, it errors, but I've patched the actual function that lets it load it up. So it now thinks the image is authenticated, even though it has an invalid DSA signature. So at this stage, I could save it to onboard flash disk. It would then be persistent across reboots. If I leave it here, the only indication and the only way of detecting the modified firmware is to take the modified firmware off the device. Although you'd really have to do a memory dump of the, take the firmware off the device and do a diff against the bootloader, which has been modified.
Could you unmodify the bootloader with this image?
I could unmodify potentially. The bootloader that they download is effectively it gets compressed when you download it into a firmware blob again. So you can pull firmware off the device, but it ends up looking like the original firmware you've downloaded from Juniper, and that everything's all compressed again. So potentially you could, yeah. And I'll talk a minute about, kind of further steps. There is some other little change I've done, really, again, just to highlight the kind of attacks that are possible and the things you could do. So now we have my modified firmware running on it, and it's authenticated as a valid image. As you're saying, what further attacks you've got. So this is the original web console for the Netscreen, which I thought was a bit dull. So I changed it to that. And I'll just type a nice big random password. That's all right. It's too big. There we go. And there's Bob. Much nicer than the existing logo. So, I mean, that's a pretty trivial change because it's images, but I think what's interesting, I suppose, is this is the proof of concept. So, as I say, we can now install any firmware. We have access to the device from any interface, and we can run any code we want that we can inject. We can call ScreenOS functionality. So really then it's thinking about what you would want to do. So at this stage, obviously if you had a config file, what you're looking at is having some hardwired, effectively shadow config or some access rules on the device in your modified firmware that say allow all traffic from your external IP through to the internal network. Or captures traffic on the higher end devices that can handle it. So at this stage, even comparing the configs of the device with previous versions, it's going to look like it's okay, and there's going to be no indication that anything has changed. Obviously, if your Juniper Netscreen starts looking like that last web interface that I showed you, it's probably not a good idea to be using it. So effectively, yeah, all the functionality that the Netscreen does, so firewall controls, looking at VPNs, all that's available for you to use. And modifying the web has, again, an interesting attack vector for escalating control. So you've got control of the perimeter device, but then what do you want to do from there? So typically it will be administrators logging into that device, hopefully on a management network. So using the web console to attack them. So, JavaScript code injection for client-side attacks on the admins, and then using maybe the Juniper to reroute that traffic back out to you is all certainly possible and would be quite fun. And then the other issue is whether we could persist the infection across upgrades. Probably not such a big issue because I don't think anybody really upgrades these. I've never seen them really upgraded, which is understandable. They're core network security devices, and taking them offline to upgrade them is an issue. But I think that's one of the things outside the talk. Out of the talk, people a lot of time are concerned about upgrade firmwares on devices and whether they'll keep working and everything. And I can assure you, this little box has had many reboots and many firmwares installed on it, a lot of which didn't work, and it's still fine. So the bootloader one's an interesting one. There's a large function in the bootloader called load ScreenOS version 4, which enables you to downgrade from the current version of 5 or 6 down to 4. It's quite big. And certainly that's a function you could overwrite and put your own code in, because I doubt it's ever really used. And I do have code for this, putting the code in the bootloader, hooking the upgrade functionality to either just prevent the upgrade but pretend it happened, or to attempt to modify the firmware on the fly as it comes in to basically give you login. It's possible, although versions, as FX talked about this morning, the issues around different versions of the Juniper firmware and whether that's easy or whether it's easy enough to find. But certainly in terms of payload, as I've demonstrated, they don't have to be that big. You know, the authentication patch is 1 bit for logging in, so not a big deal. The one thing that really prevented me implementing it is that I was pretty sure the first time I did it I'd make a mistake, and then I'd end up with a little Juniper box with a bad bootloader on it that I wasn't able to overwrite. So maybe Juniper will donate me another one, and I can complete that. So just a little bit about, I sent a white paper and modified Trojan firmware to Juniper, and with some things that I thought were flaws. You can see the response there. I did present this paper at RuxCon at the end of last year, and I think that was really what initiated them into publishing this JTAC bulletin, which is if you're a customer, you go on a security mailing list, a technical advisory mailing list, which, and they publish this ScreenOS firmware image authenticity notification, the risk level of medium. What was quite funny or scary, depending on your point of view, after I notified them, I sent it to their security guys. A few months later, got a call from a support help desk person asking me very nicely if he could help me with my problem of loading firmware. And he invited me into a view-only, fortunately, Citrix session. And he was quite happily loading up a clearly labeled Trojan firmware on a support network onto a Netscreen in front of my very eyes. So I kind of disturbed me, and then I started working out what other firmwares I could send him. So remarkably easy to social engineer people loading up Trojan firmware, and hopefully the network engineer guys are not quite as I don't know what the word is. Helpful, yes, helpful. He did seem confused that because obviously my problem wasn't a problem because it loaded up fine, and I think he was a bit confused by the different graphics on the web interface, but it's interesting for a security company and support, but I suppose that's what happens when you get too big. There you go. So this is what the JTAG says. All Juniper ScreenOS for all platforms are susceptible to circumstances in which a maliciously modified ScreenOS image can be installed. So I don't think that's a good thing. I don't want my firewall or UTM under any circumstances to have a modified firmware to be installed. So really, as I said before, I think, and I've looked at other firmwares for other kinds of appliances and devices, and I certainly think encrypting the firmware, not relying on obfuscated compression is the way to go. Even having the certificate on the device and not being able to delete it, even if it's not in hardware, obviously there'd still be ways of getting that, but just removing that command from ScreenOS to be able to delete the cert and having it installed by default at the factory. Yeah, I think crucial. So Juniper do now recommend installing the certificate file, and also their manager IP, which is effectively a way of sort of having a management network, effectively. And the last one, yeah, good luck with that. I'm not sure what that's going to stop, but yeah. They'll never find SSH if they move it to another port. So as I said, it's a, I see this really as a supply chain, or, you know, do you trust your internal admins? You probably trust your internal admins quite well, but do you trust them if you think they could install something without anyone knowing? And obviously once you have the firmware and can install something malicious, obviously there's no endpoint security on the Juniper itself. There's no way of it detecting anymore what's on there. You can do it all. I would say, yeah, limit your admin interfaces, so using SSH keys as much as possible, just to try and prevent those admin logins being able to be stolen, either passwords or what have you. And obviously have a management network. Don't be allowing people to see these interfaces on your normal networks. Limiting your administrators, and please have strong passwords. I do see a lot of very weak shared passwords on these Netscreen devices with shared accounts, and that just opens you up to these kind of attacks. So, I've been rather quick today, actually. Ripped through it. Yeah. So questions. That's all.
So you were saying you recommend that they encrypt the firmware. Are you recommending that they put new hardware encryption circuits in there? And if not, where are you suggesting that they can?
Well, it's just levels of security, isn't it? If it's in software, there's a way of bypassing it. If it's in hardware, it's harder. And if you want to get to it, you know, potentially getting keys off the hardware is possible if you're that knowledgeable. But what I've done here would have been far harder, even if they had, you know, a AES encryption of the firmware with the key stored on the device somewhere, even in software, that I wouldn't be able to get to, so there wouldn't be any commands to actually extract it or save it. Obviously, you can try to live debug it and look for it, but everything becomes a lot harder. So it's all about how hard you want to make it, and I would just say at the moment it's really not that hard, which surprised me. I expected it to be much harder, and I've no illusion. I mean, it's just me on my own, you know, it's a well-deployed device. Fortune 100 companies using it, and I expected it to be much harder. I didn't expect to be able to actually run my own modified firmware on it, and I was quite surprised when I could. So I have no illusions about if someone else had wanted to do this, perfectly possible. And you could go all the way down, as you're saying, to certificate-based, hardwired on the boards. I mean, obviously that's not going to be possible for them with devices they have. So my recommendations are really around a ScreenOS upgrade that maybe removes the delete key command, and And if before they deliver them, they install the cert on it, even that would have made my life a lot harder. So, yeah. Yes?
I agree that public key in the installed in the hardware would have been better, and the encrypted firmware would have been even better. All that is granted, and probably surprising for me that we were able to do that. Everything else, I'm not really sure. Initial mod that we did was serial cable, or for serial cable, which means you needed to have physical access to the machine.
Yep.
And where does that leave you with the attack vector? Because an attacker, unless he's an insider with access to the back-end room of the enterprise, of the 1400 enterprise, this attack is really not workable unless you have physical access.
Well, now maybe I didn't make it clear enough. I mean, once I manage that. Oh yeah, sorry. So yeah, gentleman's just asking initial attack over serial console. Where does that leave the attacker in that they have to actually get into the server room or access the actual, basically have physical access to the device to perform the attack? So initially yes, but then using my checksum calculator firmware enables me to create a firmware. So using this device, reverse engineering, I can then create a firmware which I can test on this device, and I can load that up over, basically when you log into the Netscreen, you can go to the web console, or you can, if you SSH in, you can issue effectively TFTP commands to upload a firmware across the network. Yes, so as I say, so this is, in that respect, it's a, so it talks about developing the Trojan firmware. It's not about how to exploit the Juniper box directly.
Once you're able to load any firmware, you can do anything starting from changing the logo every day to doing something very malicious. I think that's gives play beyond that. The hard part is not getting the installed box in a Fortune 100 company, and that I don't see how you've done.
Well,
That's another session.
yeah, potentially. Although I would question whether even people at Fortune 100 company. I mean, I bought this device off some supplier somewhere. I'm not even sure who it was. I stuck it on my network. I configured it, and then I put it in a crucial position right on the perimeter. So I think the supply chain's an issue because it's an easy attack. So who are you buying your box off? If I decided to become a supplier of Juniper network equipment, how hard would that be? I'm not sure. I suspect it's not maybe that hard. Or someone working in those companies.
When you buy a PC from a reseller with an infected BIOS, then the problem statement still is exactly the same.
Yes, but that's a PC, not a core network security device. Absolutely. So, yeah.
So aside from changing the images and having a shadow config, when you were in there, I guess was there any other kind of productive uses in modifying the firmware, like non-malicious, things you might want to actually change about ScreenOS?
ScreenOS.
Yes, yeah.
Okay, the question is whether it's something I want to. I think he's asking me if I want to fix anything about ScreenOS. But I don't think if I did that, I don't think you should be using anything. No, I mean there's nothing really to fix as such. It's the other implication really that I see is that because it's been easy to disassemble and also recompress and then run and test on the device, I now have effectively disassembly for ScreenOS. So in terms of actually finding, and this relates to the previous question, finding a vulnerability or an exploit on the device, anything running ScreenOS has suddenly become a lot easier because previously you had a serial console and you're just hammering away and you're trying to find an exploit, whereas now I can target things, I can see what's happening. So the next stage of finding an exploit for it is a lot easier than it would have been. So, yeah. Absolutely, and that's key. I think that's what I was saying. The main attack for me is when you inject the code, you can effectively. There's two approaches. You could either hardwire some access policies, or you can effectively, there's a function that loads up the configuration file because the config is completely separate from the firmware on the device. And it sits there and you can upgrade the firmware and you've still got the same config, obviously. And so there's functions for loading that up, parsing it, and executing whatever it finds in there. So for me, one of the best attacks is to effectively, as part of your firmware, load up have a config file, hook that load config function, it'll load up the normal one, and then also load up yours. But then on the interface, any of the interfaces, there's no way of potentially seeing that, depending on how you do it. If you stick too much to the ScreenOS commands, obviously those things would probably filter through. But if you hardwire it all, and absolutely. So as a way of gaining access to the internal network, certainly a prime way of doing it.
How big is the bootloader?
The bootloader, it's not very big, not very big. Obviously, like most bootloaders, it's pretty limited in size because it's getting, I can't remember off the top of my head. Big enough to put some functionality into it, though.
Is that fixed size?
It has an upper limit. It has an upper limit, but it's not, as far as I'm aware, it's not fixed, no. It effectively just gets taken, when it uncompresses everything, it basically takes out that chunk, sticks it at address 0 in the firmware, and, because basically you've got some flash on there that's just, divided up for stuff.
So if Juniper wanted to fix the issue, short-term and long-term solutions, the short-term will be to issue a new firmware with a new bootloader, including a certificate.
Yep.
You will load that on your device, and from then on the bootloader, every time you try to load the device, will check the certificate.
Yes.
Short-term.
Yes.
Long-term will be tamper-proof hardware containing both the certificate and the encryption key.
Yeah, well, that's kind of top end. Yeah, I mean, if they, there's various stages in there doing stuff in software, or yep, absolutely. And I suppose what's interesting is that once you get in there, it's a bit like old operating systems from way back. So there's no real, Windows, it's ASLR. Operating systems nowadays try to work out whether things are messing with stuff, while they're running. But obviously, in this, partly due to hardware restrictions and what they're trying to do, they probably don't have enough power to actually do that as well. But yeah, once you're in, it's all pretty open.
Following up to the question that somebody else asked, you kind of took it short because you did a demonstration about how to install a Trojaned firmware, but as I understand, and I'm not an expert on Netscreen, they license the different platforms, different features like maximum number of VPN time and all.
Yes.
So you could have gone into the firmware, locate that section of code, and create a EPAM.
Theoretically. But that would be licensing, and I never mess with licensing. Yeah. Okay, thank you very much. Oh, there is one little nugget I found which I thought was nice. Obviously, one of the designers of ScreenOS was called Bob, and he left a nice little comment in there, which I think says a lot about devs. Code should never reach here by design. Anyway, thank you very much.